everybody should be interested in the impact of humanity on the world we live. Yesterday, I watched Interstellar. It was this apocalyptic view of the future of our world. So
let's hope there's a wormhole nearby. Let's hope there's a wormhole nearby.
Okay, so tell us all about it.
Thank you, Ricardo, and thank you for the suggestion to talk about this topic, because you know I do both astrophysics and of astrophysics, and I was not quite sure if there would be any interest in this topic, because my impression is that many physicists don't necessarily want to hear about other topics than physics, but I'm quite happy to see that there are people in the room. And I think I should say as a disclaimer that in case you've never heard about, the Anthropocene or the impacts of climate change or biodiversity loss, it can be a fairly difficult topic to hear about. It can create a lot of very strong emotions. And I just want to make sure that at some point, if you feel uncomfortable, given what I'm going to say, feel free to leave the room, even though you have to come back, as Ricardo said. I think would be a bit weird. Yes?
Has this ever happened to you? Someone leaving the room because felt uncomfortable with their talk?
No. But I've seen people who were manifesting, a lot of discomfort, given the context. It's not a neutral topic like black holes. We're very much involved in this, and it has consequences for our lives and the lives of future generations. Okay, so I think it would be a bit strange to start this without a bit of motivation or even maybe justification, because I'm talking to an audience of cosmologists and astrophysicists. So I'm going to try to explain a little bit, where I'm coming from, how I ended up moving from caring only about black holes and gravitational waves to caring about the Anthropocene. And so I'll start with this diagram here, which is kind of a depiction of the situation of researchers today. Imagine that this circle is contains all of knowledge humanity currently has, the kind of knowledge that we may teach in schools. So maybe we should exclude, more traditional forms of knowledge. It's more like the kind of knowledge you will find in books, okay? And so if you go in one particular direction, maybe you're learning about chemistry, and here you're learning about history, and here you're learning about philosophy, say. So when you enter elementary school, you learn a little bit about everything. Then you go to maybe middle school, you learn more about everything. Then you go to high school eventually. I don't know how it is in Brazil, but in France, at some point you start specializing a little bit. Maybe in my case, I was doing more physics and math in the last year of high school. So you can see here that I'm starting to know more about physics and philosophy, okay? Then maybe you want to go to the university and you have an undergraduate degree in physics because you're now passionate about it and you almost only study physics. And you really love physics, so you want to go further, you do a master's degree and you start specializing maybe in astrophysics. And now you're getting very close to the border of what we know in astrophysics, okay? And maybe you are so passionate that you want to start doing a PhD. And for 3, 4, 5 years, you're gonna work hard, and at some point, if you work hard enough and if you're lucky enough, you're gonna make a small indent, right? New knowledge. Congratulations. You have your PhD. The issue is that now maybe your worldview looks like this because you're so into your domain, you're so hyper specialized that you kind of lost track of the big picture. So I'll remind you, the big picture is this. And I'm not, making fun of PhD students. I was a PhD student and I've done astrophysics for now, I don't know, 15 years. And I pretty much was in that situation. That was my worldview, more or less, until maybe 7 years or so. For a variety of reasons, I ended up having to get interested in what's happening down here on planet Earth. And so what I'm trying to do now is basically to be more of a generalist and trying to learn as much as I can in many topics, which, as you can imagine, takes a lot of time because you have to read scientific literature in a very wide diversity of fields. And so I was this kind of person before, I would say, and hopefully one day I could say I would be a generalist. It's a work in progress. It's a process. It's not, you know, something that you can say, I am now a generalist, of course. So why am I talking about my personal story? Because when you get interested into the Anthropocene, when you enter that field, you very quickly realize you can't just like understand what it's about if you only study climate, or if you only study ecology, or if you only study economy, or if you only study social science in general. In fact, you have to be interested in everything, and that's why it's very interesting. It's a genuinely interdisciplinary topic, and very quickly you also understand that you can't think in silos if you want to understand the Anthropocene. You can't focus just on climate or energy or minerals or food production or ecosystem, because you're going to lose a lot of connections. And when you're going to think, oh, maybe I'm going to solve climate change by focusing on changing my energy source, you're going to miss that there was going to be some important consequence in some other silo, like food production. So let me illustrate with a couple of examples. We have very convenient sources of energy called fossil fuels, which allows us, for instance, to extract phosphates, rocks, which are used to produce fertilizers to make more food for a growing population that's ideally better fed. And all this looks very good until you realize that the leakage of those fertilizers gives rise to very important pollution in ecosystems. Yeah.
Sorry, just my ignorance. What is the connection between fossil fuels and phosphates?
Well, you use fossil fuels in very big trucks that you use to extract the rock. If you don't
need to produce the energy to extract
the rock in industrial.
the source of energy that you need.
Yeah. That's just one example. I mean,
Sure.
I'm going to talk more about energy later, but you see that fossil fuels basically everywhere. It's everywhere in the room.
Everywhere.
Just plastic.
They were chemically involved in the synthesization of phosphates. No,
it's not, but it is in the production of nitrates through the Haber-Bosch process.
Okay.
So you take nitrate from the atmosphere, and you use natural gas, and that allows you to produce synthetic fertilizers, which are complementary to the phosphates that you use then in industrial agriculture. So that's a more direct with the fossil fuel. So another example, well, we know, of course, that the combustion of fossil fuels is increasing the concentration of greenhouse gas in the atmosphere, in particular carbon dioxide, and that leads to climate disruption. So we think, okay, we just have to use renewable sources of energy. And if you stop there, maybe you're an engineer, you have a well-posed problem, you're going to optimize for a solution, great. But if you think in silo, you're going to miss that to build batteries, you need to extract a lot of copper, lithium, cobalt, gallium, and so on, with lots of consequences, human consequences, but also ecological consequences, like, again, pollution of ecosystems. Maybe you can use biofuels. It's a big thing in Brazil. But if you miss the big picture, you miss the connection, you don't realize that that's going to be in competition with food production for people. Maybe you're going to do bioenergy and capture of carbon and storage. And that looks great on the paper. In a lot of the IPCC reports, it's like a big solution. But if you use it on huge scales, that's again going to be in competition with, well, basically land for other living beings on the planet.
Isn't the growth of the human population going to affect the ecosystem anyway?
It is already the case.
Yes, okay.
It's
how you feed them or whatever. I mean, if it grows a lot, the human population.
Yes.
So I don't know.
It's one factor.
The ecosystem.
It's one factor, yeah. Among many factors, because of course there's also the way of life. Depending on how much energy and material you use, you know, you may sustain a more or less big population for a certain amount of time. Yeah. These are just a couple of examples, and in fact, if you want, you can put many more arrows everywhere. The point I'm trying to make here is that if you want to grasp the full complexity of the Anthropocene, which I have not defined yet, you really need to enter a kind of systems thinking approach. And so that means also that you need to get interested in basically everything. You can't just like be a hyper specialist of some topic. Okay, so since there are cosmologists in the room, I think I'll try to give some broad context about what this Anthropocene is all about. And I'll start with a brief history of life on planet Earth, with a very nice diagram with a phylogenetic tree, where in the center you have basically the birth of planet Earth, of the solar system. Maybe 3.5 billion years ago or so, life appeared. You may have somewhere here the last universal common ancestor. And then as you go further to the left or to the right, time flows, and the present is here. And you see in this diagram this beautiful diversification of the forms of life, in particular since the Cambrian explosion 540 million years ago, with the emergence of vertebrates, so animals like amphibians, reptiles, birds, mammals, and so on. And there are a couple of important episodes, like mass extinctions. There have been 5 of them over the last 4 billion years or so, and we have initiated a 6th mass extinction very recently, as I'll mention. This is just to remind us that we tend to think of human beings as completely separate from the rest of the living world, but we're all cousins. We're all related to all those forms of life. For instance, we have a common ancestor with herring, a type of fish that dates back from 400 million years or so. And if I zoom a little bit more on that part, that after the last mass extinction, 66 million years ago, dinosaurs disappeared. It opened some new ecological niches that were exploited by mammals. And among mammals, you have primates. And among primates, you have the genus Homo. And in the genus Homo, you have many species. And the only one that's left today is Homo sapiens. And we are representative of that species. So the story continues here. And unfortunately, it looks like the 6th mass extinction has been initiated very recently. A bit more details if I just look at the last 10 million years or so. So as I said, there is the genus Homo that appeared maybe 2 or 3 million years ago that included many species like Homo erectus, Homo denisovere, Homo neanderthalus, Homo sapiens. And until just a few tens of thousands of years ago, there were several species of Homo walking on the planet. It's only very recently that Homo sapiens is the only species of the genus Homo. I don't like to do much advertising, but if you like graphic novels, this work by James Harder is really beautiful. It's all drawings, and it's telling that story, the story of life in alpha, and the story of human history in beta in 2 volumes. It's beautiful. I invite you to have a look if you want some sort of visual representation of what I just mentioned. And to address my cosmological crowd, I would like to give some cosmological perspective on, I guess, the story of our species by just showing a couple of phenomena on the left, and the typical duration or when they emerged, and then some analogies I'll explain. So let's look at the birth of the universe, the start of the universe. Almost 40 billion years ago, solar system 4.5 billion years ago, the life on Earth 3.5 billion years ago or so. The start of the mammal rule, 65 million years ago, after the last mass extinction. The first humans 3 million years ago or so. Homo sapiens has been there so modern humans for almost 300,000 years. And for almost this entire duration, 290,000 years, our ancestors have been living like hunter-gatherers. It's only very recently, 10,000 years or so, following the last interglacial age, the onset of the so-called Holocene, which gave rise to climatic conditions that allowed human beings to start innovate with agriculture, that we've seen something really new. And agriculture took over, and human societies got more and more complex with the emergence of so-called civilization. And this is a really new phenomenon if you think about the history of our species, right? This is something really new that we've tried 10,000 years ago. And now I jump even more into getting much closer to present day. 400 years ago, so basically yesterday on those kind of timescales, we started trying to understand the world scientifically with the modern scientific method, with key figures like, Francis Bacon, René Descartes, Galileo Galilei. And 200 years later, so that gave us more understanding and also more control on our environment through technical applications. 200 years ago, we found the energetic jackpot, fossil fuels. So in addition to more control, now we have more power. We have more capacity to transform the world around us. And 50 years ago, more or less, it's the onset of the sixth mass extinction, biotic collapse. So what I'm trying to illustrate here is that basically we don't know what we're doing because, for hundreds of thousands of years, we did things that worked well, which started something new 10,000 years ago. And very, very recently, we changed the way we see the world. We have a lot of power and we're basically destroying the ecosphere. So if you want some analogies, let's pretend that 3 million years is like 1 year, okay? So emergence of humans 1 year ago, emergence of modern humans, Homo sapiens, 1 month ago, the 1st of December. So all Homo sapiens until the 30th of December are hunter-gatherers, and the last day of December, they start doing something new, agriculture. And at the last hour of the last day, they discover the scientific method. So it's 11 p.m. and we start doing science. Now it's 30 minutes to midnight and we find fossil fuels, and 8 minutes before midnight, life is basically going down very quickly. So that's another way to see that we kind of doing some uncontrolled experiment and we have no idea what we're doing on a species level. I don't know if it's clear. Yeah? Okay. So in the rest of this talk, I'll mention several periods. I mentioned the Great Acceleration, which is more or less the last 50 or 70 years after the Second World War. I mentioned industrial civilization, which is more or less 200 years old. And I'll mention modernity, which you may think of as the last 500 years or so, as an historical period. So I'll come back to this. I like the citation of the ecologist and economist William Rees, who talks about us as Homo energeticus, a species out of context. And so he says that the pace of change is unprecedented. He's talking about the recent history, the last 50 years or so. The recent spurt of population, economic, and consumption growth that people today consider to be a norm actually represent the single most anomalous period in human history. I hope you're convinced about that, given what I said in the last 5 minutes. Humanity is literally converting the ecosphere into human bodies, prodigious quantities of cultural artifacts, and vastly larger volumes of anthropic waste. That's what tropical deforestation, fisheries collapse, plummeting biodiversity, ocean pollution, climate change, etc. are all about. Okay, so after this fairly dramatic introduction, I'm going to finally come into what is the Anthropocene, okay? Anthropocene is in fact a technical word for geologists that design an epoch, a proposed new geological epoch, but I'm going to use it as a more informal way to mean the age of human beings that supposedly would have started at the onset of this great acceleration in 1950. It's debated by geologists, like they don't necessarily agree on whether we should officially say we're in a new geological epoch, but it doesn't really matter from the point of view of everybody, in the sense that, the impacts are there and it makes sense to have a word to describe this, period we're living with huge impact due to human activities. Hence the necessity to have a word and the reason why the word Anthropocene is sticking, even if geologists don't necessarily agree it should be defined as a new geological epoch. So a nice definition of Anthropocene from the point of view of geologists is a proposed geological epoch said to have begun when the influence of human beings on geology and ecosystems became significant on the scale of Earth history. And if you want a little bit more detail, I have this citation from Luc Senal, who's a political scientist, in some article for the public. So he says that it has become possible to compare humanity to a new geological force now capable of interfering with the great biochemical cycles of the planet. The resulting global change may appear slow on the scale of human life. I mean, you and I, we may not see much difference on a daily basis, on a decade basis, but if you just look at, on the scale of maybe 100 years or so, over several decades, even across generations, it consists. Sorry, I'm going to read again. The resulting global change may appear slow on the scale of human life, since it unfolds over several decades, even across generations, and thus shape day by day what constitutes the most banal sense of normality. Yet on the scale of geology and evolutionary time, it reveals itself as catastrophically abrupt, and therefore compels that desiring reflection on the meaning and consequences of the industrial venture, if not on the very fate of the human species itself. So here's a kind of overview of the biophysical landscape today, and I'll just, give you a bit more details about some of them, but I don't want to spend too much time on, say, describing, the fairly dire biophysical situation. I want to spend more time trying to understand how we got there. So in terms of energy, I'll mention the fossil fuels used, of course, and the so-called carbon pulse. I don't know if you're aware, but the so-called peak of conventional oil was already clear 20 years ago. It was back in 2006 that we had the maximum use of high-quality oil. That's admitted by the International Energy Agency. Since then, we've still increased our consumption of oil, but it's using so-called non-conventional sources of oil, which are of lower quality. There's never been any past energy transitions, only additions and synergies among different forms of energy. So we'll see that. Regarding climate, I'll mention anthropogenic climate change, maybe this issue with cooling of aerosols, which makes the situation worse. The possibility that we may tip several subsystems of the climate system through positive feedback loops with a risk of a runaway climate change to so-called hothouse Earth. I think, kind of a very rapid increase in mean surface temperature with very dire consequences in case we, inadvertently tip some of those subsystems to a new state. And regarding more broadly ecology, accelerated erosion of biodiversity, plunging population across species and taxa. Just if you think about the insects, I think in Great Britain, there is a recent measure, there's a loss of something like 70, 80, or 90% of the mass of insects in the span of a few decades. So it's at the, very basis of the food chain, insects, right? That has consequences for birds and many other species. It's important for pollination also, if we want to eat something else than rice and potatoes. The onset of the sixth mass extinction, a situation of sustained ecological overshoot for more than 50 years, and many transgressed so-called planetary boundaries. So I've read now maybe hundreds of papers on those topics, and I'm not going to bother you with all of it. I just want to say the situation is really, really, really dire. Like we are here, talking about black holes and galaxies and so on. It's super fun, but I think it's really time to wake up and start thinking, why are we even doing this if this is going to stop, maybe in, I don't know, 10 decades or maybe a couple of centuries? What will happen to all that knowledge? And is anybody going to benefit from that knowledge? Because if we keep going as we do, it seems pretty unlikely that there'd be any astrophysicist in a century, to me at least. So let me illustrate with a few points. The Anthropocene. So Anthroposphere versus biosphere. Nowadays, there's twice as much carbon in the form of human-made plastic than there is carbon in the living biomass. Nowadays, the mass of all the buildings and human infrastructure is larger than the total mass of the dry mass of trees and shrubs. So that's what it means to have a planet which is really just for human beings. Okay. So that diagram is showing the increase in this anthropogenic mass which is the sum of the mass of all concrete aggregates, bricks, asphalt, metals, and other stuff like plastic and so on as a function of time. You see it increasing very quickly, as I said, after the 1950s, at the onset of the Great Acceleration, and that's more or less equal to the total dry biomass around today. You can also look at, the resulting biomass, in particular in animals, in particular in mammals. How is it distributed? When I read books to my daughter, there are many wild animals everywhere. It's beautiful. But when you look at the situation today, there's like almost 400 megatons of humans, 8 billion of us. There's twice as much domesticated animals, not quite, but a lot. So that's the cattle. And most of deforestation is basically to grow that cattle. And then you have the wild terrestrial and marine mammals. So the wild mammals, like elephants up here, it's like less than 2% of the total mass of land mammals, if you include humans and the cattle. So that's another way to understand that we are making this planet into our own image, in the sense that it's just for us. There's no space for wildlife anymore. Let me move now to the climate. So maybe you've heard about the fact that for the last 2 million years or so, there's been oscillations in the climate with so-called glacial phases that come after interglacial phases, with a typical period of 100,000 years or so. And these change in the climate, interglacial phase or glacial phase, is very deeply connected to the concentration in greenhouse gases in the atmosphere. So dioxide of carbon, methane, nitrate oxide, and some others. And here I'm showing the concentration, the atmospheric concentration in carbon dioxide in parts per million over the last 800,000 years. Most of that data is ice core data taken from Antarctica. And then you have the modern data of the last 60 years or so. And what is really remarkable is that for millions of years, this concentration in carbon dioxide has oscillated between 180 and 280 parts per million. And in the span of 200 years or so, we've managed to increase that concentration by more than 50%.
So,
yes?
could there be a systematic effect? Because modern data are taken with a different approach than ice core data, are they?
Well, it's a different way to analyze the data, but I mean, of course, the people who are studying this are looking for systematics and making sure that they get to have curves which are talking about the same thing, right? But the difficulty that I'm not going to mention is that depending on the scale on which you have a look, the causation between increase or decrease in concentration on just carbon dioxide and average mean temperature goes one way or the other. It gets quite subtle in the sense that when you look at the short-term dynamics, it's the increase in CO2 that is driving the increase in temperature. But when you look at much longer timescales, the causation can go the other way around, or at least it's more mixed.
No, but my question was how is it measured the modern measure of the concentration of carbon dioxide? How are they made?
Ah, you mean currently, like so in the atmosphere, you just measure the concentration atmosphere. Yeah, but you just do it in a place which is very clean in the sense of far away from any disturbance. In fact, you don't want some industry that's producing CO2 nearby. So typically, you can do it in Hawaii, on the top of the mountain, Monaco, for instance.
And I mean, basically, people do this thing. They guarantee the ice core data and the sample of present atmosphere, and they are monitoring the same.
Yeah.
Okay,
Yeah, I don't know the technical details, but yeah.
You still figure that they should give the same result. See what.
Yeah, no, I still.
And what causes those oscillations? What caused them in the past? And where does the carbon dioxide?
On that time scale, so these are called the so-called Milankovitch cycles, and that's related to orbital parameters of the Earth. like the eccentricity, the obliquity, and some third parameter I forgot.
So like the distance to the sun or something could be.
That doesn't change much, but the eccentricity has. It's due to small perturbations in the motion of planets in the solar system, and so you can model that, and you can see the correlation with the evolution of the mean temperature, and that then correlated to the greenhouse gases as well.
Where does it go to when it goes down? What does it mean? I mean, what is
You mean
the carbon
here,
dioxide?
for instance?
Yes.
So here is a time 20,000 years ago or so, the last glacial maximum, when the temperature was about 6 degrees lower, and the physical state associated with this mean temperature corresponds to a much lower concentration in greenhouse gases.
Okay, so it's the temperature that oscillates and that causes that the carbon dioxide is.
So that's what I was mentioning to Ricardo. It's the causation is fairly complicated depending on the timescale you look at. In the short timescale that we have today, the causation is quite clear. You increase the greenhouse gas, you have radiative forcing, you increase the temperature. But when you look at this kind of timescales, actually you have radiative forcing due to astronomical phenomena that is affecting the mean temperature, and that then is going to affect also the chemical composition of the atmosphere, which you see here.
But then the carbon dioxide, where does it go? Is it absorbed by biomass into the ocean?
Into the ocean, essentially. But I don't want to spend too much time on that diagram, but the key point I wanted to make is like this planet with 6 degrees less has nothing to do with what we have right now. The mean level of the sea is 120 meters lower than today because you have huge polar caps. Okay, so this is not the same planet as this planet. And it took 20,000 years to go from here to here. And in the span of 200 years, we've done this. And half of that increase was done in my lifetime, in 40 years.
It's really the forecast.
So in terms of physics, what we're doing is we're kicking the climate system very violently.
So the lower temperature also increase the size of the polar cap, so this subtract water to the ocean. But also the
It
temperature,
subtract water to the ocean.
yeah, it also just thermal expansion.
Yeah, but that's a smaller effect.
That's small.
Well, let me skip that. That's more controversial, but it's interesting. The situation could be worse than the IPCC suggests, depending on the size of the cooling effect of the aerosol that we also emit in the atmosphere. But that's still open to debate, so I'll skip it. A more important point, it's not that we have, a problem with climate and we're waiting for a solution with an energy transition. Climate change is one symptom among many symptoms. And so a broader, I guess, framework would be the planetary boundaries framework, where you look at many properties of the Earth system, including climate. The idea here is that for any of those 9 subsystems, you have some regime where you know that the biosphere is healthy, you stay close to the condition of the Holocene, where our ancestors were very happy, say. And you have a control variable for each of those subsystems. For instance, the CO2 concentration when you look at climate change, or the radiative forcing. And if the control variable is close enough to the value it had during the Holocene, you're in the so-called safe operating space. But if that control variable is getting way out of that range, then you get out of that safe operating space, and the further out you go, the more dangerous it gets, in the sense that you may shift the Earth system to some completely different state. So you see here that, in terms of climate, we're way out of that safe operating space. It's also the case for the integrity of the biosphere in terms of genetic and functional diversity. It's the case for land system change, think basically deforestation to produce more cattle. It's the case for the destabilization of geochemical flows of phosphor, nitrate, and water, of course. Novel entities, that's basically chemical pollution, including plastic pollution, but not only. And the only thing where things are still more or less okay is basically ocean acidification, which is one consequence of emitting CO2 in the atmosphere, which is, still in the safe operating space, according to this group of Earth system scientists, and the aerosol loading of the atmosphere and the depletion of the stratospheric ozone layer, which are still okay. But you see that basically the situation is pretty bad. And if you look as a function of time, it gets worse on a daily basis.
In recent years, some years ago, actually, the ozone depletion was
That's the only counterexample, indeed.
also the aerosol, because they were saying that it was because of this aerosol
That's-
that was making the hole in the ozone layer.
So you're correct to say that if you look at the situation in the 80s or the 90s, so that would have been worse.
Oh,
So maybe it was there. I don't know, maybe it got better thanks to the Montreal Treaty. And this is getting better in the sense that we are polluting less the atmosphere through aerosols, but there is one consequence, which is that these aerosols are in fact having a cooling effect. They're reflecting some of the light. And so if you have less of those cooling effect, you have more climate change. So that's what I wanted to skip, but basically depending on the size of that cooling effect, the so-called Faustian bargain of James Hansen, instead of 1.2 degrees of average increase over the pre-industrial temperature, maybe we're already more than 2. Maybe the Paris Agreement is already broken if you take into account that effect. But that's still, you know, discussed among climate scientists.
The ozone thing, for instance, says that when, you know, community states want to take action,
Yeah.
you can get some results. That's the good point that you can take.
Yeah, but if you enlarge the, you know, the focus and you look at, you know, how difficult or easy it was to have that agreement, you see it's just one particular industry. In the case of climate change, you have to change the very foundation of industrial civilization, which is the use of fossil fuels. And climate change is just one aspect. It's way more difficult to, basically what I'm saying, it's way more difficult to deal with all of this than just that.
Sure.
Way more difficult.
But it's not impossible.
Well, let's see. Let's discuss this. I hope not, but it's not obvious. So you could argue it's not new that, you know, human beings are affecting their biotope or interacting with it at least. There have been long-standing anthropogenic impacts, even like tens of thousands of years as the Homo sapiens was, you know, basically colonizing the planet. It was basically extinguishing the megafauna along the way. It's only in Africa that the megafauna survived, maybe because Homo sapiens appeared there and so co-evolved with the megafauna. The domestication of crop and livestock and the spread of agriculture dates back to, you know, thousands of years. And the forest clearance, the erosion of soil, and the modification of the atmospheric composition are also processes that, you know, started a long time ago. So this is all correct from a qualitative point of view. But the key point is that quantitatively, what we are doing is very different. We now have the energetic means to change the planet in such a way that the consequences are quite drastic. We're basically, you know, confronted to the fact that the planet is finite, which was not the case before. So this is why we may talk about a so-called great acceleration following the World War II. So 70 years or so, the onset of this great acceleration, which you can see by looking at the trends on many indicators of the Earth system or even socioeconomic indicators. So I mentioned the atmospheric composition, but you can look at the ocean acidification, tropical rain, forest loss, domesticated land, the degradation of the biosphere, and so on, or the use of primary energy, the growth of the population, in economic terms, the global GDP, and basically all indicators are, you know, going through the roof starting in the 1950s. So that's why some geologists are suggesting that this Anthropocene epoch should officially start basically more or less in 1950. Okay, so that was, I guess, an introduction to what is the Anthropocene. But this term Anthropocene is very unsatisfactory because it kind of flattens out everything. It's saying, oh, it's, you know, the fault of human beings. But which human beings? I mean, whether you're an indigenous in the rainforest or Elon Musk, you don't have the same impact on the planet, of course. And also, as physicists, we might say, it's, you know, how do you end up being capable of transforming the planet this way? And so an alternative lecture could be a so-called Carnocene. So it would be the age of fossil fuels that maybe started something like 200 years ago when we started using increasing amount of coal. And so on that diagram, I'm showing the global primary energy consumption as a function of time over the last 200 years. I don't know how many of you have seen that figures before, because there's a lot to tell in that figure. No one has seen it? Yeah, no? So you see all the energy sources and the quantity we use in petawatt hour. And you see, the first thing you see is that it cumulates, right? You have the traditional biomass. That was the only energy source we used until 200 years or so. Then we started using more and more coal, and we added oil on top of that, and natural gas on top of that, and hydropower and nuclear, and the so-called, you know, renewable energy sources. You can barely see them on that diagram, like wind and solar and modern biofuels. That's because 82% of the primary energy we use today is still fossil fuels, coal, oil, gas, and every year we use more of it. That's what I mean by there's never been any energy transition before. We keep adding more and more energy and using more and more of it and diversifying the types of sources of energy. But we're not replacing fossil fuels with so-called renewables. In fact, to produce the infrastructure to exploit renewable energy sources, we need fossil fuels, at least until now. And so the onset of this acceleration, I mean, from a physics point of view, it makes sense to say the driving curve is more energy because that's what drives all economic activities. You could really think of fossil fuels as the energy pillars of modern society. So as I said, it's like more than 80% of the primary energy we use. And we use it to drive the so-called world economy. And that world economy, that activity economy has consequences. It generates forms of pollution, including gas pollution, which is driving the climate out of dynamic equilibrium. And it degrades ecosystems. So I already mentioned all of those things. But what I'm trying to say is that, you know, the world we used to, the world around us, was made possible thanks to fossil fuels. And all of it depends on fossil fuels until today. If you don't like that situation, because you don't want climate change or you don't want max extinction, I have good news for you. We're not going to keep using fossil fuels forever. Simply because there's a finite quantity of it. At some point, we'll go through a maximum of use of fossil fuels. I mentioned that for good oil, so-called conventional oil, the maximum was already 20 years ago. Since then, we have not used any more higher quantities of good oil. We're using more and more non-conventional oil to substitute for the fact that we are reaching geological limits. So I apologize for that diagram. I didn't have time to translate it from French. That's the only one which is not in English. But I think it's very easy to read. In green, you have the curve showing the discoveries of conventional oil. Okay, you have some peaks depending on how much you invest in exploration. But the important point is that the peak of discoveries was more than 60 years ago. Did you know that? Because sometimes you hear, you know, there's always more discoveries, we never run out of oil. Well, as a matter of fact, in terms of good quality oil, for a long time now, we're not making as much discoveries as we used to. And once you have discovered sources, you may start producing, exploiting those fields. And that's the curve in red here. Okay. And as a good physicist, you know that the integral of that curve in green has to be equal to the integral of that curve in red if you exploit everything you've discovered. And that gives you a finite number. And so that curve will necessarily pass through a global maximum, after which it will decrease eventually with like secondary maximum, but there will be a global maximum. And one important question is, when is that global maximum? For good oil, it was 20 years ago. For the total oil consumption, it's an open question. Maybe it's going to be tomorrow, maybe in 2 years, maybe it was last year. I have not looked at the latest data. Maybe it will be in 20 years. Maybe it will be in 40. I don't know. But it's not going to be in 100 years or 200 years. It's going to be in our lifetime.
What about non-conventional? Because you mentioned that, but it's
Yeah.
not the trial.
Yeah, so it's on that plot. So on that plot, you have a split between, field oil, offshore, where you go, 500 meter to 1 kilometer below the ground in water, deep offshore, oil sands, which are non-conventional oils, shale tight oil, which is also non-conventional, and so on. So here you have a split, and the good oil, you see, it's here, and it's never gonna keep increasing.
It's
Because
interesting to see the going down during the pandemic.
Oh yeah, you can see. So you can see the first shock oil in 73, the second shock oil in 79. You can see the 2008 financial crisis a little bit here, yeah, and you can see the COVID pandemic here. After that, it's modelization. This is data and this is modelization. The key point of that diagram, though, is not so much the split between conventional and non-conventional. The key point is that to extract energy, you need to use energy, right? And the important point is this yellow here, which is the energy required to produce energy. So what this is showing you is that we're using more and more of less quality energy, in the sense that we need more and more energy to extract energy from our environment. And in this modelization, the scientists have predicted that in 25 from now, half of the energy we extract from the environment in the form of oil will be invested to extract more energy. So then only half of the energy is useful for application in society. While in the 70s, all energy was useful, because you just make a hole and the oil goes out. So that's not discussed either, but it's a very important point. What fraction of the energy is actually useful for society?
But some time ago, I heard about this fracking process.
Yep.
It was terrible. Is
Yeah.
it there?
Yeah, that would be in shale type oil. Shale oil is the oil you extract through horizontal fracking. And you see that it's a significant fraction since 2010, essentially, from the US.
So it's still going.
It's still going, but it's not going to go forever either. Okay, so big picture again. Let's look not at, decades or hundreds of years, but thousands of years. What is the history of use of energy by humanity? Well, basically, until the Industrial Revolution, you can't see anything. It was muscle and wood. And on a scale that saturates to 1, we use barely no energy at all. And then you have the use of fossil fuels that goes up. It will necessarily go down, probably on a characteristic time scale comparable to how fast it went up. So maybe, a couple of hundred of years. Maybe it will go down faster, who knows? But it will more or less look like this on that scale. And up to a few years or a few decades, we are more or less at the top. So it's a very special time to be alive as a human being. We have the privilege of contemplating history, not from the top of a pyramid in Egypt, but from the summit of a global peak oil or global peak energy.
This is the fossil energy or oil energy.
Well, it's more or less the same thing.
Well, okay.
It depends on what's going to happen after. I mean, if you're a nuclear physicist to think, you can replace all fossil fuels by nuclear, and that's going to keep going like this, I think you're kind of deluding yourself, but that's what people thought 50 years ago. But if you look at all the constraints, physically, economically, geopolitically, etc., I don't think that's going to happen. No one knows what's on that side, but I don't think the curve is going to go way more up than what we
Sure, no, but what you mean now, 20% of energy is not fossil, say.
Sure.
So that 20% will stay or increase, in one batch.
Well, that 20% is mostly hydro and some nuclear and some wind and some solar, basically. And the key point I was making is that to develop all those, we've been using fossil fuels. It's not clear to me that when you have no more fossil fuel, you can still build nuclear plants.
Into a centrifuge. to verify uranium, that takes energy.
For instance, but there are everything. I mean, the construction of everything, everything. It's a very, very complex system. But that's become very speculative. I just want to remain in the realm of what's clear. What's clear also is that the energy transition will happen. The question is whether it will be voluntary or whether it will be compulsory. But since, there's a finite quantity of fossil fuels, either we use almost all of it, and then climate change become completely out of control, and I don't think civilization can survive that. And so at some point you won't have the means anyway to extract more fossil fuels from the ground because it becomes more and more technically difficult. And so if the climate is very unfriendly, that won't happen. Or we decide maybe before that we should stop this, and then we transition to other forms of energy. But it will happen, that's for sure. Hopefully voluntarily, not compulsorily. And I will end this part on energy with a diagram I made, which I think colleagues in the social sciences will not like very much because I'm kind of naturalizing a lot of social, cultural, and political phenomena. I'm basically reducing everything to energy, which of course the physicists like to do, but there's a lot of things which are not accounted for by energy in the human world. It's just that I find it very compelling, this diagram. It's an energy-based view of history, where as a function of time, very schematically, I'm showing how much power we have at our disposal in human societies. And it's kind of like a bifurcation diagram in dynamical systems. So imagine you have, human societies that have used slowly more and more energy per unit time. At some point, they make a technical innovation, they control fire. Well, Homo sapiens is still there, knows how to make fire, but Homo ergaster is not. Homo ergaster knew how to use tools with rocks, but not how to make fire. I'm not claiming that disappeared because of that, but it's interesting observation. Thanks to fire, maybe you have access to more power, and then you invent agriculture. It doesn't happen like this. It has taken hundreds or thousands of years. It was very inhomogeneous, complicated, very complicated dynamics. But at some point, if you look on the long time scale, you see that agriculture people have displaced hunter-gatherers, and nowadays there's almost no more hunter-gatherer people on the planet. And all of us almost can live thanks to the produce of agriculture. Still further in time, a new way to organize ourselves socio-economically, let's call that capitalism. In Europe, that was not very good for indigenous people in America. Still a little bit more forward in time, the scientific method, in particular with applications in the army, new kinds of weapons. And so a form of superiority when it comes to make war, that was not very good for the populations that got colonized by the Western world. Then fossil fuels, and you get closer to the global situation today, where basically you have a global north that's still exploiting the global south. Yes?
Why capitalism tends to get below scientific method? Isn't that like very, very much correlated, or at least?
According to some historians like Fernand Braudel, you could pretend that capitalism goes back to the 14th century. There's been different phases of capitalism. You're thinking industrial capitalism that goes hand in hand with the use of fossil fuel and primarily coal. But there was a merchant phase of capitalism before that, which was driven not by industry at that time.
But the scientific method will be Galileo, isn't it?
Yeah, I mean, the thing is, you can't really determine like by a date when those things started, but you could argue that, it would be the 15th century, 16th century, something like that. Yeah. So I would tend to say that capitalism predated by a little bit the scientific method. But yeah, of course, to a large extent, they co-evolve together, especially since the industrial phase of capitalism.
You take it as landmark, the institutional banking system.
For instance, yeah, in Italy. Yeah. And that dynamic cannot go on forever unless, you know, artificial intelligence become super intelligent and starts colonizing the galaxy, and then planetary boundaries are not an issue, but that's not clear it's going to happen.
So
So that's out of the diagram.
Yeah, that's something I was going to ask about artificial intelligence.
Yeah.
Not that, but the fact that it's using a huge amount of energy.
Yeah.
Is that a concern? Maybe you should talk about this later, but I've seen data centers.
Yeah, it's still of the order of, you know, a few percent. So it's not like, you know, a quarter,
Okay.
but it's growing exponentially. So, and now those companies are even wanting to build nuclear plants specifically dedicated to give energy for data centers. So yeah, it is an issue, of course. Yeah. Yep.
What is the meaning of global south and global north?
Yeah, so that's a term that are often used in social sciences to describe what before we would call, you know, third world countries or developing countries. It's kind of vocabulary, developing country and underdeveloped country or developed country. It's kind of a vocabulary used by basically European nations, the US, countries that industrialized first to describe, you know, different countries. It's very ideologically driven, in my opinion, and I think nowadays in social sciences, people tend to talk about more global north, global south, which has less of a kind of judgment, like, you know, something is superior and something is inferior, and the inferior thing has to get to the stage which is superior.
Yeah, but once that I mentioned global south or something, I said something about China.
Yeah.
People were, because I guess China is in the global south. And people were saying, well, China. So I don't know. I mean, it's hard to find
Exactly.
the border.
It's very hard because it's super simplifying. Like you have like two camps, right? Global north, global south. It's too simple. So it's always an issue to choose your words. And this diagram is super is very much a simplification of reality, of course. So time is flying. How much time?
I mean, if you're too hungry, you can leave it as much, but I mean, it's very interesting. I mean, let's go.
Yes, they.
So that was the least interesting part. The best has come. Because we're gonna enter now more into the deeper roots and deeper causes.
I mean, provided we deal by June 30, it's fine.
Okay. So maybe I'm gonna skip the Anthropocene because it's a little bit of a joke. But the key point I wanted to make is it's not okay, sure, you have a lot of energy, but you know, it's not sufficient by itself to have a lot of energy. You need to use that energy to produce useful work. So you need some technical device to have an effect on the world. And so clearly the Carbocene doesn't capture that dimension. The Anglocene captures it in the sense that it's insisting on the fact that it's in Great Britain that the industrial mode of production first appeared and then spread first through Europe and then to the rest of the world during the 19th and 20th century. And it's a process that's still ongoing. It's not over yet. But the key point is that you need, you know, technology, and in particular the, I always forget how to say machine à vapeur in English. What? Machine à vapeur. Thank you. Thank you. So the steam engine that was used in particular to produce fiber in England, in Manchester, in the first factories, is a technical device that allows you to convert energy into useful work. So the key point is that it's not enough to have energy, you need to be able to use it. And then the Industrial Revolution then plays a key role in understanding the dynamics of the Anthropocene. If it's just to make fun of English people or some of their colonies like the US or Canada, it's okay, it's fun for a French person, but I don't think it's so interesting. It's more interesting if you try to understand what were the historical, geographical, and socio-political conditions that made the Industrial Revolution possible. And then, of course, you need to go to some key authors, like, for instance, Karl Marx and his theory of primitive accumulation of capital. So if you look at historically what happened in England during the 16th, 17th, 18th century, there was the so-called enclosure of common lands. So most people had no more access to the resources that they used to reproduce their life on a daily basis, and had then to move to cities and work in those first factories. And that's the onset of then the first working class. And that's a consequence of some political decisions that were made by some people at that time in that place. So it didn't happen by magic. There was some socio-political conflicts going on. You can also look at the role that the transatlantic slave trade played, because it's not good enough to have steam engines and coal. You also need to transform something, for instance, cotton. And who is harvesting cotton in the fields? Well, the slaves in America. So this primitive accumulation of capital was kind of the start that allowed for the diffusion of the industrial mode of production. And it's important to contextualize this diffusion by looking at what happened. The dimension of imperialism, the British Empire, colonialism, the French Empire, for instance, plays a key role here also as well. And even today, it keeps playing a role. If you look at, for instance, the so-called world systems theory of the sociologist Wallerstein, he emphasizes the existence of a core of country, a semi-periphery, and a periphery with some unequal economical and ecological exchanges, which is always to the benefit of the core countries and to the detriment of the countries in the periphery. So this kind of unequal exchanges and dynamics of exploitation are still happening today. It started a long time ago, but it's not over. So I think that's a less known one, Econocene, the age of economicism. What I mean by economicism is basically economic reductionism, to reduce basically all of social activity to economic activity that you can theorize, that you can mathematize, and then you pretend that you understand the world. And I use the date 1871 because this is the onset of the so-called marginalist revolution, which is basically the moment that so-called classical economy or political economy becomes a mathematical field in a school of economics called the neoclassical school. And that gave rise to what one might call today orthodox economics, which is almost all of economics. There are many schools of economics, but orthodox economists who use a lot of math are basically, everywhere in economy department and also speak to the ears of politicians and they give advice and so on, while heterodox schools of economics are much less represented and have much less influence. And the point I want to make here is that the diffusion of the industrial mode of production was a material process, but there were some theories and ideas behind that, were helping this going on. And neoclassical economists, orthodox economists, help this process of diffusion by building some theories that, in my opinion, are completely disconnected from physical reality or biophysical reality. So if you think about the system of economic production, here's the theory. If you ask orthodox economists, you have households and businesses. And of course, the businesses provide goods and services to the households who provide labor and capital, because of course, human beings are human capital. And those households can buy those goods and services thanks to the wages, because they work in the businesses, and that gives spending for the businesses that can reinvest part of the money to grow their businesses. And you can make the picture a bit more complex by adding banks with money coming in through savings and investment, money coming out, governments who tax and spend, and eventually trade between countries. But if I show you this diagram, I think you will not be much surprised. Like, that's what economy is, right? It's flow of money between households and businesses with institutions, eventually state institutions. Okay, so the economy, the sphere of economy has households, markets, the state, eventually commons, even though they play not a very big role nowadays.
So what is commons?
Commons is things that belong to no one or to everyone, like the atmosphere. Or like what used to be land that belonged to everyone in England before the Industrial Revolution, and then was closed, and then just belonged to a few people, and then the people could not, you know, get wood to make fire, and they had to move to cities and work for factories. So that was a common, the woods in England in the Middle Ages, for instance. Okay, that was a joke. This is not correct. This is not economy. I mean, economy is part of a bigger system with inputs which are completely crucial. To have an economy that works, you need a society with human beings. In fact, economic activity is just one part of many sorts of activities in societies. You have many more dimensions in a society than economy. You have juridic dimensions, you have political dimensions, you have religious dimensions, you have many dimensions. Economy is just one part of it. And human societies are embedded in the Earth system. And in the Earth system, you have energy coming in and energy going out. And you're not going to have any sort of economic activity without incoming energy, mostly fossil fuels, and incoming matter, living matter and materials that you get out of the ground. And that economic activity is producing waste heat, but also waste matter that provokes pollution that ends up in the ecosystems. So it's obvious for a physicist or for a biologist, but apparently for an orthodox economist, this is completely irrelevant. It doesn't matter. So they have a vision of the world, which is, in my opinion, very problematic. And you can measure this. I'm not just making a claim. I mean, in this paper, the people are following, you know, the flows of the extraction, production, consumption, and production of anthropic waste from 1900 to nowadays. So you have extraction, I don't remember, I think it's gigatons of fossil material, biomass, metals and minerals. You process that material, you use energy, you use materials, eventually you construct stuff with the material, and that ends up also producing emissions like solid, liquid pollution and gaseous pollution, including water vapor, which is not necessarily considered pollution. And eventually you have some recycling of matter or downcycling, the quality decreases after every recycling. And you can track the evolution as a function of time. So that was 1900, now it's 1945, 1973, 2002, 2015. So more and more extraction, production, consumption, and reduction of pollution. And this is because this economic system and the theory that's behind it says that we need a growing economy, which is almost linear because you have less than 10% recycling, but it's happening on a finite planet. So if the flows are very small, doesn't matter that the planet is finite, but as they become very big, you start feeling the boundaries and you have all the consequences I mentioned at the beginning of the talk. Yes?
So, from what I understand, you are kind of proposing a new type of economy that not only takes into account the money cost of labor, transport, but also the energy cost of extracting resources from nature.
Well, it's not that I am proposing this. I'm just saying if you want to understand the way the world works, you need to account for material and energetic inputs and outputs. And that's not something I'm discovering right now. I mean, there's a heterodox field of economics called biophysical economics or ecological economics that has been knowing this for a long while. Unfortunately, you know, even though, of course, they are way more grounded in reality than orthodox economists, they are a very small community among economists.
Mm-hmm.
Yeah. So the way orthodox economists treat the natural world and human beings is everything is capital. Natural resources are capital. They are natural capital, forest, fisheries, minerals, and people are capital, human capital. So natural capital is decreasing, human capital is increasing, there's more and more of us. And thanks to those two things, we're producing more capital. And that's something which is measured by orthodox economists, particularly Das Gupta, who's quite influential in England, with data taken from 140 countries. So if I had to summarize with one picture, the way I see the world is more like this. I think most human beings see the world this way. But if you're an orthodox economist, with your theories, this is the way you see the world. It's pretty problematic. Everything is capital that can be used eventually to grow the stock of capital. So this idea, well, green growth is an oxymoron. I'm going to skip this. I'm going to come to Capitalocene. I ended the Econocene part, which was kind of an idealist way of seeing the problem, in the sense that the problem is certain ideas which are wrong. Now I'm coming back to a more materialist understanding, where I'm saying the problem is the way we materially organized.
Now let me ask you, because now
Yeah.
we are seeing the rise of China,
Yeah.
which in theory is not capital. Well, I don't know. Well, how
I would
could
say
you
it's
find
a
China?
form of state capitalism.
Yeah, state capitalism. So China also follows all those types of behavior
Sure.
with respect to the
Sure,
to the planet.
sure, completely.
Because it seemed very much your description very Western oriented.
Well, it's the same.
Plus-
It's the same in Brazil. It's the same
I
everywhere on the
understand-
planet
I'm
now.
understanding Latin America for sure. But I mean, in the past, there was the Soviet Union, which is
Sure.
different. But
No,
the
but
way they exploited
it is the same.
was the same.
Was the same. And we're gonna understand why, because there is an underlying relationship to the world which is common. That's gonna be after Capitalocene, when we're gonna talk about the Occidentalocene.
Yeah, but for example, the Maya Empire, apparently, it fell because they exhausted their resources.
All
So
previous
there was no
civilizations,
capitalism
all
really.
previous civilization collapsed. There's no exception to the rule.
So it's human behavior.
Not so sure, because there are many human groups who were in way more harmonious relationship to their environment. And as I said, you know, human behavior is hunter-gatherers for almost the entire history. Hunter-gatherers didn't have the means to transform the world into a supermarket, and they didn't.
But once you settle, it's like, I don't know, you start because you are in a particular
So
place and
you-
need to use that.
You're anticipating on the last slide, and I'm not I'm not gonna claim, you know, there's a fatality here and there's nothing we can do about it. I'm unclear. I keep changing my mind all the time. But I think it's a key question, yeah. Whether once the settling dynamics and agriculture starts, it's necessarily gonna end up this way or not. I'm not sure.
Because
But what is
you say
yeah.
that imperialism, colonialism was a driver for
Sure.
this growth and
For
stuff.
the-
So
for-
it's
yeah.
because they were, and I mean, their resources were coming to an end, and so they went out to look for other,
Yep.
at least in England, because I don't know,
Well,
you also see that
for
the
most countries in
capitalism-
Europe, yeah.
Yeah, but Spain and Portugal was not capitalism then, but they went out also.
I think they were part, according to some historians, they were certainly part of a global trade at that time,
Mm.
in the 15th century, and 16th century.
Mm.
So, but I don't know if it's going to be satisfactory, but I'm not going to claim the final point is that the problem is capitalism. I think,
No, 10 minutes too.
okay,
Otherwise, we don't have time for lunch.
yeah. So capitalism, I think, has to be, how do you say, dépassé.
Exacerbation of the devastation, I guess.
For sure. I mean, the way it's organized and with the energy we have, it accelerates the devastation. But doing something else doesn't guarantee you're not going to still do the devastation. So it's a necessary but not sufficient condition to go beyond capitalism, in my opinion. Okay. So what is it exactly, capitalism? many people disagree on the definition, but there are some common points like private owning of the means of production and the existence of markets on which you have companies that can compete to sell goods and services. But the way I want to define it is more general. Like on that diagram, I'm kind of showing, you know, some dimension of the Earth system, like energetic, climatic, ecologic aspects described by the natural sciences, and some aspects of, let's say, modern human society, like economic, social, cultural, and political aspects. And for lack of a better word, I'm using tools for things which are very different, like technology, finance, media, and minerals. So one thing that capitalism is an economic mode of production. So of course, economy and finance play a role. But it's also a very specific socio-political organization. So society and politics play a role. In particular, you need the state to impose the respect of the propriety rights through police and army. Since the industrial phase of capitalism, capitalism is a techno-capitalism in the sense that technological innovation plays a key role. And as we've seen, to grow the economy, you need energy input, but also matter, so extraction of minerals. But capitalism is also an ideology, in particular, since the end of the Keynesian phase, we've entered the neoliberal phase of capitalism. And so culture and media play a key role in the diffusion and conservation of capitalism. So I think all those dimensions are important to define capitalism. And what remains is climate and ecology. And what are those for capitalism? There are externalities. They are external to the logic of capitalism, which is to maximize profit. And that's the reason why we have climate change and ecological devastation, or approximate reason for why. So here I want to argue, following an heterodox economist, Anthropocene Poitier, that capitalism and ecology don't work very well together for a variety of reasons. Because capitalism has embedded in it an objective of profit maximization, it has a structural imperative for growth, it externalizes the ecological costs, it has a short-term thinking, a logic of substitution. When you're lacking of something, you replace by something else, a lack of cooperation because everyone is competing. Of course, the free market trade comes first. That's even official in the Convention 4 des Nations Unies. I don't know how to say it in English. It's written. There is an incentive for consumption. We're all subject to advertising, of course. And there is the making of Homo economicus. I didn't mention, but for orthodox economists, Homo sapiens, I mean, we are basically all sociopaths. The only thing we care about is being happier by having more consumptions of goods and services. We have no other dimension in our existence. And so we're trying to maximize our so-called utility. And of course, historically, this is not true, but one can be worried that culturally we tend to make people like that in the society we currently live in. So this is my opinion. It's not something I think I've demonstrated, but given everything I've been able to read and understand so far, I think that sustainability on the long run is fundamentally incompatible with this mode of production. And more probably with any socioeconomic system which is predicated on the continuous expansion of energy and material throughput. So you mentioned the ex-Soviet Union. There was a lot of extraction of energy and material from the environment in those countries. And so again, going beyond capitalism is a necessary but not sufficient condition to avoid this disaster. Okay, and since I'm almost out of time, I'll finish with maybe the most interesting one. Occidentalocene, the age of the West, or Western modernity, which maybe we can say starts with the Columbian exchange in the end of the 15th century. The idea here is that capitalism is not the ultimate reason for the disaster. You have to understand how capitalism came to be and how it is connected to all the dimensions of Western societies. So industrialism is not the ultimate reason, capitalism is not the ultimate reason. Maybe some particular way of being as a civilization, so-called modernity, is. And In the social sciences, modernity is kind of a debated concept, but there are some key characteristics that we can identify and agree with. In terms of socioeconomic organization, at least the late modernity is characterized by the capitalist mode of production, by industrialism, urbanization, the importance of nation states, the increasing importance of bureaucracy, as well as control and surveillance of societies, the societies. The cultural foundations are individualism, universalism, and naturalism. So by individualism, I don't mean being egoistic. I mean the importance of the individual, right? The individual is important, not just the role it plays in society. By universalism, I mean ideas like, the Declaration of Human Rights and Citizen, which didn't include everybody. The women were not included. The slaves in the colonies were not included at the end of the 18th century. But you can think of the United Nations Universal Declaration of 1948, right? So that's what I mean by universalism. And naturalism is an ontology. Anthropologists identify different kinds of ontology in different kinds of human society. You can be totemistic, you can be animistic, but you can also be naturalistic. And modernity is characterized by a naturalistic ontology. And
I don't understand this word, naturalistic.
naturalism as an ontology, I'm going to talk about it in 2 minutes.
Would it be related to science?
It's very much related to the way science works. I'm going to come to discuss it, because we are very much concerned by that. I mean, we are completely into naturalism as physicists and as physicists. There's a cultural dynamics of secularization and rationalization, in the sense that, well, the religious ideologies are losing ground, while the secular ideologies are gaining more prominence, including political ones. There are a number of characteristic values which are professed. I don't think they are applied, but they are professed, like justice, liberty, equality. And the three key political ideologies of modernity are conservatism. In reaction to conservatism, there was the emergence of liberalism in the 18th century, which was revolutionary at that time. And due to the excess of liberalism in the 19th century, there was the emergence of socialism in the historical sense. I don't mean social democracy. I mean what was called anarchism or communism at the time. And we can connect all of those. In particular, we can see how capitalism, industrialism, and nation states, and how they're so important for modernity, are related to those cultural foundations. So I'm showing this on the diagram. I have those three important dimensions of the socioeconomic organization of modernity and the cultural foundation. We can give a bit more detail about capitalism, property rights or importance, extractivism, productivism, consumerism. We can add some more intermediate steps, like modern science is going to be kind of a link between this naturalism, ontology, and industrialism, but also liberalism and the philosophical doctrine of utilitarianism played a key role to the emergence of capitalism in relation to the importance of the individual. And then you can put lots of arrows to understand basically how things are connected, and how, capitalism is not something that appears out of nowhere. It's also related to some cultural foundation that characterize modernity. I have no time, so I'm not going to detail it, but I think it would be interesting to do so. And to answer Ricardo's question, what is naturalism? It is the ontology of the moderns. It's our ontology. It is the way we understand the world. And the way we understand the world is that there are two different things. That's the realm of the non-human, and we call that nature. And it's universal. It obeys laws, the laws of physics. And if you have a reductionist outlook, you could even say, you could derive the laws of chemistry and biology and ecology out of the laws of fundamental particle physics. That's what I mean by universality, and we call that nature. And there's something else, I've completely disconnected, nothing to do with it. We call that culture. It's the real of humans. We are beings of culture, and there are many cultures. And then it's characterized by a multiplicity of cultures. And these two universes are considered to be completely heterogeneous and irreducible one to the other. This is without thinking about it the way we think about the world on a daily basis. Even the way we organize science reflects this, because how do we study nature? By doing natural sciences. And how do we study human societies? By doing social sciences. In particular, anthropologists study the diversity of cultures of human societies. So it's reflected even in the way we organize knowledge, this naturalistic ontology. And the key point is that we are subjects as human beings, and we can study objects, and we consider nature to be an object, to be objectified, to be understood through the prism of science. I discovered this very recently. To me, this is kind of trying to be self-reflective. It's like trying to understand your own relationship to the world. And until you actually realize that, in a sense, you're kind of blind to your own activity, I think. And so this is a problem because it's a very anthropocentric worldview in the sense that we have on the one hand man, on the other hand nature, and you can have men against nature or men and nature or men in nature, but certainly not men, by which I mean human beings, as nature, as being part of nature. I started this talk recalling the tree of life because in our ontology, we are not part of nature, right? Man is a subject that can conquer, beat, transcend, exploit, subjugate, own, dominate, control, protect, or even enjoy, explore, appreciate, or study an object, which is nature. This is the way we live. This is our ontology. We grew up in a society which has this ontology. And there are other ontologies. I think I have to stop, so I'm gonna. Yeah, maybe I'm just gonna. Can I just read this?
Yes.
So this guy, Tom Murphy, is an astrophysicist. All of his career, he's been sending laser beams to the moon to measure the Earth-Moon distance with a very accurate measurement. I think maybe a centimeter or millimeter, and that allows you to test the strong equivalence principle in particular. And very recently, he had a kind of intellectual awakening. I don't know how to qualify it. At least he followed the path which is very analogous to mine, and now he calls himself a recovering astrophysicist. So here's what he tells us. Humans are a biological species, one of millions, relatively new to the planet, needed by few but needing many, part of nature, belonging to Earth and no other place. Moreover, many humans on the planet are only very recently experimenting with modernity. Recall the context I tried to give earlier. Operating without explicit regard for ecological consequences, rapidly spending a material inheritance, boasting a population temporarily swollen on the fruits of that inheritance, carrying out enormous ecological damages as a thoughtless byproduct of energy and material expenditures, running a system predicted on something as obviously inherently unsustainable as growth, purposefully decontextualizing our lives by separating further from nature because of the naturalistic ontology, powerful enough to have initiated the six-mass extinction, collectively arrogant enough to think we're getting away with it, short-lived enough to not appreciate the magnitude of insanity, unaccustomed to thinking about context as life are increasingly structured around our concerns. And I remind you, we are hyper-specialized as astrophysicists and cosmologists. That was my last important, I guess, I don't know how to say, grid lecture. So I'll skip it and I'll just conclude.
Oh shit, many things and interesting things.
Oh, maybe you can share your
Slides.
slide.
Sure, I can share. Sure.
And also it's online, the talk, so it will be online. The principal chat.
And so here is a summary, right, of all of it. It started 10,000 years ago with agriculture. Then you can see what happens. At some point, we end up having the real enlightenment with science, and then we have more energy. And now everything is going out to the roof. And so I started discussing the Anthropocene with a great acceleration 50 or 70 years ago. Then we talked about the Carlocene, the importance of having a lot of energy. If you go back a bit more in time, look at the Diocene, which was not the ultimate explanation. Then we talked about the Occidentalocene, and there science plays a key role, and the naturalism as an ontology. But we could go way back in time and mention the Anthropocene, which I had no time to explain. And well, I guess I'll stop here and I thank you for your attention.
Okay, we had quite a few questions, really happy to speak quite a lot. Let's see, comment or question. Okay, I'm sure this is not the last time we discuss about these topics, and
I hope so.
thank you, Alex.
Thank you.
Thank you.
Let's be